Okay, this is the implicit differentiation problem. It says consider this curve here. Show that this is the derivative. This is implicit differentiation. So what you need to do is you need to dx the entire thing, which is x squared plus 4y squared equals 7 plus 3xy. Okay, so the derivative of x squared is 2x, and the x is matched, so you don't have to do an x prime or anything. Now the derivative of 4y squared is 8y. The x and the y don't match, so you need to multiply it by y prime, equals the derivative of 7 is 0. This is a product rule situation. Two functions, 3x and y. So the derivative of 3x is just 3, and the plain old second is y, plus the plain old first, which is 3x. Now the derivative of y is 1, but we're ddxing the entire thing, remember, so the x and the y don't match up, so we need to multiply by y prime. Anytime you have an implicit diff problem, we want to solve for y prime, that's the derivative. So I'm going to get them together on the same side. 8y, y prime, minus 3xy prime equals 3y minus 2x. I just rearrange some things algebraically. Now, always with implicit diff, we're going to factor out a y prime. We get 8y minus 3x equals all of this garbage over here. And then we're just going to divide both sides to get y prime by itself, which is 3y minus 2x all over 8y minus 3x. So that's A. A had to show that that's the derivative. Oh, there it is. Okay. Now B says, show that there is a point with x-coordinate 3 at which the line tangent to the curve at that point is horizontal. Find the y-coordinate of P. Okay? So I'm looking for a point with x-coordinate 3 at which the line tangent to the curve is horizontal. Okay. Here's our derivative. So that's the slope of the tangent line. If the tangent line is horizontal, that means that the derivative is equal to 0. For a fraction to be equal to 0, that means the numerator is 0. So I'm looking for a spot where 3y minus 2x equals 0. Okay? They tell us the x-coordinate is 3, so I'm going to stick in 3 for x, and I get 3y minus 6 equals 0, so y equals 2. So the point P is at 3, 2. That's the point where the derivative is 0. Honestly, what you should do to check to make sure the point even exists is to plug 3 and 2 in here and see if the point actually exists. And what will happen is if when you plug in 3 and 2 here, this should be a true statement. So if I plug in 3 and 2, plug in 3 for x, 2 for y, 3 for x, 2 for y, what you end up with is 3 squared is 9, plus y squared is 4 for the 16, I plugged in 2, 7 plus 3 times 3 is 9, times 2 is 18. Is this a true statement? Yeah, it is. So the point 3, 2 exists. So there it is. Okay. Now let's try C, which is the trickiest one. C says, okay, so find the value of, this just means the second derivative. So we're looking for the value of the second derivative. Okay. Here's the first derivative. So what I want to do is I want the second derivative, so I'm going to ddx the derivative, which is 3y minus 2x all over 8y minus 3x. Okay. Well, it's a quotient rule situation. Derivative of the top is 3y prime, because the variables don't match, the x and y, minus 2 times the plain old second, which is 8y minus 3x, minus the plain old first, which is 3y minus 2x, plus the derivative of the second, which is 8 times y prime minus 3. I'll try to get that in. Okay, there you go. And that's all over the denominator squared. Okay. So that's the second derivative. Now the question was, we have to find the exact value of it at the point found in part B, which is at 3, 2. So we're going to plug in 3 for x, we're going to plug in 2 for y. But wait a second, we have these y primes in the second derivative. Well, at the point 3, 2, what is y prime worth? Oh, it's worth 0. So anytime I see a y prime, I'm going to plug in 0. So I'm plugging in 3 for x, 2 for y, and 0 for y prime. Let's see what happens. So I get 0 minus 2 times, plug in 2 here, I get 16 minus 9 is 7. Minus, now watch, Plug in 2 for y. 3 times 2 is 6, minus 2 times 3 is 6. Look, this becomes 0. 0 times anything is 0. So this all becomes minus 0 all over. Let's see, plug in 3 for y. Right, is it 3? Oh, I'm sorry. Plug in 2 for y. So 16 minus 3 for x, 9 is 7. 7 squared. So this becomes negative 14 over 49. You can pause and check the algebra if you want, which is negative 2/7. So the second derivative is worth negative 2/7 at that point. Okay, so let's go back to it. The question is, does the curve have a local max, a local min, or neither at the point P? And we have to justify our answer. So at 3, 2, here's what we know. We know the first derivative is worth 0, and we know the second derivative is negative 2/7. So if the first derivative is 0, there are sort of 3 possibilities. Tangent line is 0, so either we've got that situation, I'm going to call A, we've got this situation, I'm going to call B. There is theoretically one more situation where we have a horizontal tangent line that looks like this. That could be that situation, C. So how do we determine, do we have A, B, or C going on? So do we have a min, do we have a max, do we have a min, or do we have neither? Well, the first derivative is 0. Look, the second derivative is negative. So that means it's concave down at that point. Of A, B, and C, look which one's concave down. Oh, it's A. That means it's a max. Boom. You're done.